Hello students. So in the previous class we started with Frobenius method, but I concluded up to pre-final step, you can say. So we'll continue the discussion and we'll start where we left off. If I recall, then we had derived up to this point. So we wrote rho square. This was our equation required for the series solution of that type, which we wrote. So rho square plus p 0 minus 1 into rho plus q 0 equals to 0, since c 0 was not equals to 0, right. Now this particular equation, first of all, this is called as indicial equation, right. In that previous example where I wrote indicial equation, this is that indicial equation that we are talking about. Now from here, this is a quadratic equation, so we will end up getting 3 solutions, right. So those 3 solutions can be, first of all, distinct and not differ by an integer. Then second case is may be equal, right, and third case is may be distinct, but differ by an integer. So first of all, what will happen to the first case, right? So what will happen to the first case is that we have say distinct. So case 1, we have distinct roots and not differ by an integer. So if that is the case, so let us say we have rho 1 and rho 2, 2 roots, and they are not same, and also rho 1 minus rho 2 is not an integer, right. If this is the case, then basically we put rho 1 and rho 2 for rho in equation number, so in the previous class it was, I believe, equation number 8, where we had y is equals to x to the power rho into c 0, then we had c 1 by c 0, then c n by c 0 and all that. So that is our expression number 8, and I can, so this equation, where is that? Equation number this, so this one actually, this is our equation number 8, right, from the previous class. Okay. So and then of course I mentioned 3 cases will arise. So therefore here rho 1 minus rho 2 is not an integer, and we put rho 1 and rho 2 for rho in equation number 8. So first you put rho 1 and then you get one solution, then you put rho 2, then you get one solution, and we drop the constant, and we drop the constant c 0 and get 2 series solution, first one will be y 1 x to the power rho 1, then we will have 1 plus x f 1 rho 1 plus x 2 x square f 2 rho 1 plus dot dot and so on, and y 2 will be x to the power rho 2, then we will have 1 plus x f 1 rho 2 plus x square f 2 rho 2. This is from equation number 8 from previous class, and this, and therefore the general solution is y is equals to a y 1 plus b y 2, where a and b are arbitrary constant. So if the roots are distinct, then it is very easy to write down the general solution. Since it is a second order equation, you need both y 1 and y 2, that means 2 independent solution, and this is what we are getting. When the roots are same or maybe equal, then it sort of gets little bit messy in a way. So, suppose case 2, let rho 1 is equals to rho 2. In this case, there is only one value of rho, but we need 2 solutions, right. So, there is only one value of rho which gives one series solution, but an equation of the second order is expected to give 2 independent solutions, right. So, we need to look for another solution. So, here we take some help of, we take help of something that is coming from Wronskian, that how to get the 2 independent, if you have 2 independent solutions, then the Wronskian must be non-zero. So, more or less towards the similar line, we will get the another solution or another independent solution in the following way. So, what we are going to do, we put y is equals to some c0 into some w, where this w, x is equals to x to the power rho 1 plus x into f1 rho plus x square into f2 rho plus dot dot and so on xn fn rho plus and so on. Okay, let us go to the next page. Then what will happen? What will happen is, we will end up getting this d square w. This is what we did in the previous example, but it is just that the method itself is so long, I only focused on the example, but now you can connect that example with this lecture. So, d square w by dx square plus capital Px into dw by dx plus capital Qx into w equals to rho square plus rho into P0 minus of 1 plus Q0 into x to the power rho minus 2, which is basically rho minus rho 1 whole square x to the power rho minus 2, because rho 1 equals to rho 2. So, we might as well take rho 1 minus rho 2. So, we have taken rho is equals to rho 1 equals to rho 2. Now, this is one equation, I do not know, this is equation number, we call it as equation number. If I have not given any equation number, then, or maybe I can call this as 9 and these two as, or maybe this one as 10. So, then this will be our equation number 11. So, again now we differentiate both sides of this equation. So, if we differentiate both sides, then it will become d square by dx square, derivative will go inside, and this will become px into dw ddx of dw by dx. No, we differentiate, sorry, we differentiate with respect to rho. So, this will be ddx of dw by d rho plus qx into dw by d rho. We are differentiating with respect to rho. So, differentiating with respect to rho, and then on the right hand side we will get rho minus rho 1 whole square dd rho of x to the power rho minus 2 plus 2 into rho minus rho 1 into x to the power rho minus 2. Let us call this as equation number 12. So, from 11, thus from 11 we see that W is a solution of the given equation if rho is equals to rho 1, and from 12 we see that dw by d rho is also a solution is also a solution of the equation if rho is equals to rho 1. So, and because the right hand side of both 11 and 12 equation, because the right hand side of both 11 and 12 vanishes when rho is equals to rho 1. Obviously, because if you put rho is equals to rho 1, then this will become 0 and this one will become 0, because rho 1 and rho 2 are same actually. So, what will happen is we will get d square by dx square of w plus px into dw dx plus qx into w equals to 0. So, w is a solution, and same thing is happening to dw by d rho. So, basically we have w and dw by d rho as the two independent solutions. So, hence the first, therefore, w and dw by d rho are the two independent solutions. So, therefore, we will evaluate w at rho equals to rho 1, whatever we will get from here, and so that is x to the power rho 1, and then what I mean, say we can write actually the expression. So, let us write it anyways. So, we can write x to the power rho 1 plus into 1 plus x times f1 rho 1 plus x square f2 rho 1 plus dot dot and so on, and dw by d rho will become x rho 1 log of x into 1 plus x of f1 rho 1 plus xn fn rho 1 and so on, rest of the term whatever we will get, right. So, from here dw by d at rho equals to 1, right. So, whatever we will get, we will call it as w2, and the required general solution will be then the required general solution will be then a is equal y equals to a w1 plus b w2, where a and b are arbitrary constants, right, arbitrary constants which can be determined from some other conditions like initial condition and so on. So, as you can see, if the roots are equal, then the whole methodology changes. When the roots are distinct, but they are differ by an integer, that is really long, the derivation. So, we will skip that part, but if you are interested, you can definitely look into the textbook. That is the third case, right. So, third case is the roots are distinct but differ by an integer. So, this is a little bit lengthy part, so we will skip that one, but at least now we know the example that we have covered in the previous class, what was it about. Let me just recall that example so that you can also connect with it. So, we will skip the major calculations, which is that we will just I will just show you what we did in that example, right. So, if I am not wrong, I think we had this example. So, solve. So, this example we had. So, solve the differential equation, x square y double dash minus of x y dash plus x square plus 1 into y near 0. So, of course, near 0 it is singular. So, So, it has a singularity at x equals to 0. So, the solution is singularity at x equals to 0. Then we take the solution y as x to the power rho summation n running from 0 to infinity c n x to the power n as equation number 2. This one is equation number 1. Then we put everything back into the equation, that is that one, and then we keep on simplifying. So, when we simplify, we ultimately get this indicial equation. So, as I showed you that the indicial corresponding to n equals to 0, the coefficient of the lower degree term was C0 into rho minus 1 and minus of C0 rho plus C0, and the indicial equation that we had was C0 into rho minus 1 whole square. So, from here we got rho equals to 1 1. So, this is still better. If we have roots not differ by an integer, that is also better. But if it is differing by an integer, that means if we get root as 1 comma 2, then it will become very lengthy. So, we got our indicial equation, we got the roots are equal, and that is why we have to construct that w. So, we took w equals to so we constructed y, and y was C0 into x to the power rho 1 minus x square by rho plus 1 whole square plus x to the power 4 by rho plus 1 whole square rho plus 3 whole square. Just recall that expression. So, we had an expression of this type which we assumed C0 into w. This was our w, including this one also. So, this one was our w, and then we saw that it will satisfy that ordinary differential equation 1. So, it will become x squared w double dash plus minus x into w dash plus x square plus 1 into w equals to rho minus 1 whole square into x to the power rho, right. So, this is basically our w equation. Similarly, we can do dw by dx, and we say that at rho equals to 1, it actually becomes a solution. So, therefore, both w and dw by dx are the solution for rho equals to 1, and therefore, you evaluate w at rho equals to 1, you evaluate dw by dx at rho equals to 1, and then you write down the solution as y equals to a w1 plus b dw by dx dw by d rho at rho equals to 1. So, we did that, all these things. It's just that the theory followed in the next 2 chapters, and yeah, this is a series solution. So, it is definitely not so easy to calculate the series solution when you have a singular point. When you are doing it for ordinary point, it is very simple. You are just doing an infinite series expansion, and then you are equating the coefficient. When you have singular solution, that is when the things gets a little bit tricky. But nevertheless, there is a nice flow chart, I would say. So, you you identify the singular point, then you take that expression, then you put that expression, then you get the indicial equation. Now you know the roots of the indicial equation, depending upon whether the roots are distinct, not differing by integer, or equal. You have 2 particular methods. When the roots are distinct, but they differ by an integer, I did not cover that part because it is relatively lengthy. So, we will skip for now, but you can look into the textbooks. It is just that the calculation is analogous, it is just that it is little bit lengthy, nothing more. Okay. Now, hopefully you will find some examples in the assignment sheets, and you should be able to solve them. My intention is to talk about something called a special function, right. So, from here I will now switch to something that is related to special functions, which is like Bessel's function, Legendre polynomial, things like that, right. So, let me just so today again or in this class I will have less time to cover the Bessel function and Legendre polynomial, but I will try to give at least some introduction. So, let us go to the next slide. So, special equations or special functions. So, special functions. So, they are called special functions because they have a very nice applications in applied mathematics, right. So, let us say we have this equation x square y double dash x plus x y dash x plus x square minus of n square y equals to 0, where n is a non-negative real number. It is a non-negative real number. So, r plus, of course, union 0. So, it is a non-negative real number. So, obviously, this has a singularity. So, there is a singularity at x equals to 0. This is called as basically Bessel's differential equation, and what we are covering is, or what we are starting now is the Bessel's function or Bessel's polynomial, whatever seems appropriate to you, Bessel's function. Bessel functions. Okay. So, in this case we can obtain the general solution by Frobenius method. We can obtain the solution by Frobenius method, and at x equals to 0, and this is y equals to ay1 plus by2. This is our Frobenius solution by Frobenius method, where a and b are constants, a, b are constants, and y1 is x to the power n 1 minus x square by 2 square into n plus 1 plus x to the power 4 2 to the power 4 2 factorial n plus 1 n plus 2 minus and so on. And similarly, y2 is equals to x to the power minus of n 1 minus x square by 2 square 1 minus n plus x to the power 4 by 2 to the power 4 factorial to 1 minus n 2 minus n minus and so on. So, basically looking at these two expressions, we can say that at least they look like a polynomial, but you can actually bring it into a very nice form, right. So, let us multiply y1. So, we multiply y1 by 1 by 2 to the power n gamma n plus 1. This gamma is basically our gamma function. I hope you are already familiar with, and denote the function by Jnx, right. Thus, Jnx will be summation r running from 0 to infinity minus 1 to the power r factorial r gamma minus of n plus r plus 1 into x by 2 minus of n plus 2r, right, n plus 2r, and this is n plus r plus 1, sorry, minus 1 to the power r factorial r gamma n plus r plus 1 x by 2 n plus 2r, and j minus of n x will be summation r running from, this is r by the way, do not get confused, r to infinity minus 1 to the power r factorial r gamma of minus n plus r plus 1 x by 2 to the power minus of n plus 2r. Here it is minus of n. So, now this is called as Bessel's function Bessel's function of first kind of order n, of first kind of order n, and if n is not an integer, then this is basically our Bessel's function, right. Okay, Bessel's function of first order of first kind of order n. Now, we have these two expressions, and if n is not an integer, so here we can write if n is not an integer, then we have j minus of n comma x. The second solution will be this one, right. Okay. So, now we have written the Bessel functions. Actually, there are several properties of Bessel functions that is also important here. So, I mean there are a lot of properties, but we will just summarize few of them, and we will show that how they are actually relating to our given differential equation, and then we will move on to the Legendre polynomial, right. It is just that so the derivation would be, I mean the next derivation would be slightly lengthy. So, we will introduce the Legendre polynomial in the next class itself. So, we will conclude the lecture here itself, and in the next class we will start with the Bessel functions. We will start with these two expressions basically, and then we will look into some properties. We will summarize those properties. Proof we will skip probably, and then we will introduce the Legendre polynomial, and we will also, Legendre polynomial has a lot of properties. So, we will summarize some of those properties, and then we will move on to our next topic, all right. So, thank you for your attention, and I look forward to you in the next class.